Hi. First of all, I would like to thank the organizers of the SIAM conference for this opportunity, and also thank you who are choosing and listening to my talk. My talk today is about the effect landscape fragmentation on Turing pattern formation. First of all, I start my talk with some motivations. First motivation is about habitat fragmentation. Habitat fragmentation means that the landscape, because of different causes such as human activities and natural events, is divided to the smaller patches with different characteristics and quality. A main feature of fragmented landscape are edges separating different patches. For example, as we see in figure 1, our landscape is divided to two smaller patches. The one of them is forest, the other one is grassland, and this edge between these two patches is called interface. Such edges can have a number of effects on population densities and distributions. The other and the last motivation for my talk is about patterns. Any repeated arrangement with certain regularity in space or time is called pattern. Pattern widely exists in nature. For example, the wave on the surface of the water, or even as we can see in figure 2 as well, the stripes and spots on the animal's skin. The pioneering work of pattern formation was conducted by Turing in 1952. And also the study about Turing patterns were originally started in chemistry because of interactions among chemicals, and later it also was studied in developmental biology. Then we have my outline, as you can see here, and my talk is divided as a two main parts based on the type of the landscape, the homogeneous landscape and heterogeneous landscape. And my goal here to discuss and provide the model and discuss about the Turing pattern formation on these types of the landscapes. I know that Turing pattern formation is just defined for homogeneous landscape, but we'll see how can we define and how can we study Turing pattern formation on heterogeneous landscape as well. First of all, homogeneous landscape. But first of all, before to start to see that how we get Turing pattern formation, I would like to give a very brief summary of the mechanism of Turing pattern formation. Turing's study was originally proposed in chemistry, as I mentioned earlier, but his idea has quickly spread to ecology. I will mention that why we can also study Turing pattern formation in ecology a little bit later. But to get Turing pattern formation, we have to have two fundamental properties. First one is that we need to have two substances as an activator and inhibitor, which they have positive and negative effects on each other. The other one, we have to have difference between these two, in fact, movements of these two substances. We have to have a slow diffusion for our activator and fast diffusion for our inhibitor. Once we have these two fundamental properties, we can follow the mechanism to get patterns. In fact, if we have an activator, it pushes itself up, as we see here, and they are too close of each other because of a small dispersal that we have for our activator. On the other hand, the inhibitor spreads faster and far as they can to stop the activator. This mechanism leads to get pattern. The associated spatial pattern is named a Turing pattern. In fact, as I mentioned, we can study Turing pattern formation in ecology as well, because in ecology we have interaction among species and also between species and environment. So as long as we have enough movement, we can get Turing pattern formation under this basic Turing pattern mechanism. Here we wanted to study, we are going to study Turing pattern formation in ecology, and we wanted to focus on one of the most important interactions between a species as a predator and prey. So as the next step, we create our model. We consider our model as a predator-prey model and discuss about Turing pattern formation in terms of equation for this type of model. So as we see here, we have denoted our prey by U, and we have denoted by V our predator. The movement behavior and population dynamics for each of these species are described by these reaction diffusion equations, and also we have no flux boundary condition in order to make sure that no individuals cross the boundaries of the landscape. Then we wanted to study Turing pattern formation. So as a first step, we need to consider the time-independent problem of system 1 to find the coexistent steady state, which is denoted here by U star and V star. And then we have this following condition, which should be evaluated at the steady state and guarantee that we get Turing pattern formation with this predator-prey model. These conditions, the first two conditions are necessary conditions, and they comes from in the absence of diffusion that we have a stability for the especially homogeneous steady state, and the last two conditions are sufficient conditions where in the presence of diffusion the especially homogeneous steady state is unstable. The last two conditions also, the threshold value for the ratio of dV over du, which is the ratio of the diffusion of our inhibitor over activator, gives us the value as a critical diffusion. And once this ratio is greater than the critical diffusion, satisfy these two inequality, the last two inequality, as to make sure that we have enough movement to get patterns. So we have to have generally these four conditions to be evaluated at the steady state. Once all to be satisfied, we can get Turing pattern formation for our model. Here, we focus on one of the most and famous predator-prey model, which is called the May model. We have this non-dimensional May model, and our domain and our landscape is denoted by omega, and our prey population density for prey by U and predator by V. And then we have this following reaction diffusion equation that describe movement behavior and population density for our prey and predator. Our prey can grow logistically, and we have this perturbation for our prey, and predator also grows logistically with this intrinsic growth rate S and carrying capacity QU. And also we have these no flux boundary conditions as we see in our system. To study Turing pattern formation, we have to have, first of all, coexistent steady state, and then we need to evaluate those four conditions. Then we see that by fixing our parameters, somehow to satisfy those four conditions, we get patterns formation for the May model. Here I'm focusing here on these two parameters, Q and D. Q, make sure that we have activator in our system, and this ratio should be greater than 1 and greater than that critical diffusion to make sure that we have enough movement. Then we see that based on numerical simulation that I've done, we get pattern formation for our prey as we see on the left side, and for our predator on the right side. We can discuss about some more details about the critical wavelength and so on, but here we have not enough time to discuss about such these details. Already, honestly, we know that the main model does patterns in the homogeneous landscape, but my project is about doing this in habitat heterogeneous. So here we have heterogeneous landscape we consider infinite periodic landscape with alternating patches. Patch 1 is denoted by omega 1, and population density on patch 1 is denoted by U1 and V1 for our prey and predator respectively, and similarly for our predator and predator on patches 2, which is denoted by omega 2, and our population density are denoted by U2 and V2 for our prey and predator respectively. And then population density and movement behavior are described by reaction diffusion. On patch 1 is similar to what we had for our homogeneous landscape. On patch 2, because in fact patch 1 is a good patch for our prey, so they can grow, but on patch 2 it's also we can say that it's a bad patch, so our prey can't grow here. So we replace this growth function with this linear dead function here for our prey, and the rest is for our predator is similar as we see, because the bad and good patch for in terms of our prey, it just depends on prey abundances. Then we have no flux boundary condition, the same reason as before, but we have interface, and we have discontinuity at the interface here, which depends on this probability preference. Alpha u means that the probability preference for our prey moves to patch 1, and 1 minus alpha u probability preference of our predator on patch 2. Similarly, we have these probability preferences for our predator denoted by alpha 1, alpha v, and 1 minus alpha v. And we impose, and at the interface, we impose matching condition for population density and flux that were derived from random walk model, were derived by the random walk model by Ovaneskian and Conan, and studied further by Messil and Luce. So we have this setup for our model, and we wanted to discuss about Turing pattern formation. But first of all, we wanted to be able to discuss about Turing pattern formations, but for heterogeneous it's not possible. So we use the advantage, and we use these tools, which is called homogenization technique, to find the homogenized model, which is pretty similar to the homogeneous model. So to do that, we consider two spatial scales. We have a slow or large scale spatial variable for our original model, and then we have fast or a small scale spatial variable on local environment. Then we model the spatial temporal dynamics at the fast scale according for variation in movement behavior and population dynamics arising from local environmental heterogeneity. Then by scaling up, we can obtain a model in terms of the slow scale variable that we wanted to study here. And this is the relationship between fast scale and slow scale in homogenization technique. So the reason is that, and the goal of homogenization here is to obtain an approximate model that describes the slow scale behavior of the system by appropriately averaging the variation in movement and growth parameters over the landscape. By doing this, we come up with the homogenized model, where the coefficients of the resulting homogenized model are constant. And these coefficients of the homogenized model are the average of the coefficients of the heterogeneous models. And this average is not the simple arithmetic means. It's more intuitive, and we have to use mathematical theory to find these coefficients, which are average of our coefficient of heterogeneous models. So we come up with this homogenized model, and because the homogenized model is the homogenized model is much more easier because the coefficients are constant, and easily we can analyze it analytically and numerically, as we did to answer these two following questions. So in fact, we had these two following questions to answer in our heterogeneous landscapes. These are if we get patterns on both types of the landscapes, but not on the other one. If we put them together, could heterogeneity lead us a pattern? And the other question to answer is that if the pattern formation conditions are not satisfied on both types of the patches. So for example, on the patch 1, it's possible to get patterns, but if we have no activator or not enough movement, so we don't get patterns. And because we don't get patterns on patch 2, we wanted to answer this question: when we put them together, could lead to all conditions to be satisfied to get patterns because of in the effect of the heterogeneity or not. We answer this question by using the following by these numerical simulations. For the first question, when we have patterns on one of the patch on patch 1, so we have we have activator and we have enough movement, but we don't get patterns on patch 2. When we put them together, we see that we get patterns because of heterogeneity. As we see, we get patterns for our prey on the left side of this figure, and we get patterns for our predator. As we